Hi everybody and welcome to another lecture for our machine learning course. Today we'll be talking about convolutional neural networks, and in doing so we are taking another big step in the direction of the current state-of-the-art architectures. Let's get right started. Before we talk about theory or anything like that, let me first give you an overview about where we are topic-wise. So in this lecture, we are dealing with machine learning, which is a subset or subtopic of artificial intelligence. You probably remember this graphic from the start of the lecture. So far, we've been mostly dealing with classical machine learning algorithms. In the last two lectures, we introduced the perceptron, the multi-layer perceptron, and feed-forward neural network architectures. And then we talked about backpropagation and optimization. So how can we optimize those networks? Now we're moving into a topic that's even more, or a subtopic that's even more specific, namely deep learning. And the introduction for deep learning basically already took place in the last lectures, where we talked about how we can build deep feed-forward neural networks. So why is this field called deep learning? Basically the idea that we already tried to get across in the last lectures is we can stack any layer, a number of layers that we like, and not of nonlinear activations, and we can do that to build increasingly deep networks. So in the classical MLP, you would only have an input layer, then some intermediate hidden layer, an output layer, and connect that to a loss layer. But as I said in the first lecture about MLPs, there's no reason we have to restrict ourselves to one hidden layer. We could take as many hidden layers as we want to build a very deep network. And in doing so, we would basically already be doing deep learning. But the question is, so with the feed-forward neural network structures that we know so far, is this actually useful? And I'm sure if you did the last exercise sheet where you had to build a neural network to predict that zip code data set, which by the way is also known as MNIST, you probably already tried out different architectures. So I'm sure some of you tried not using just one hidden layer, but using 2 or 3 hidden layers maybe. And well, if you do that and try to train your network, you probably found something like this. Here I set up an example with a very simple feed-forward neural network architecture, and basically just linear and sigmoid layers stacked on top of each other. And so you can see that when we use one hidden layer, we don't have any plateau over here. We go right into the training, and at some point our loss saturates and our network starts converging. And for 2 hidden layers, we also have a similar behavior, but here we have a plateau phase that's a bit more pronounced. And the training seems to be taking longer to converge, and it's not even clear that the training loss is going to be smaller than the training loss for the network with 1 hidden layer at the end. And this is certainly not the case for the network with 3 hidden layers. So in other words, it doesn't seem like just adding more hidden layers to our feed-forward neural networks is helping us with our problems. And this is a bit frustrating because how are we supposed to get deep neural networks if we can't just stack layers to get deeper models? And it's also surprising from a historical perspective, because if you, for instance, you look at the ImageNet competition winners over the years. So here I've done this for 2011 to 2015. You will notice that the number of layers used in those networks has been constantly rising, and in fact there has been a literal explosion of the number of layers here from 2014 to 2015. And well, this is surprising because how did people manage to do that? I mean, here AlexNet, for example, has 8 layers. We can't even get 3 layers to work. So how does that work? And well, there's a couple of things, or there's a couple of key developments from my point of view that have helped usher in this explosion of layer depth in convolutional or in neural network architectures. So let me give you a quick overview of the history leading up to this development. So in the 1960s, David Hubel and Thorsten Wiesel, both Nobel laureates, by the way, did extensive research to map the structure of the visual cortex. Now this may seem a bit far off topic-wise, but so just as with the artificial neurons and the biological neurons, there's also a correspondence between convolutions and structures in the visual cortex. And of course, this should not be taken as a one-to-one correspondence, but it's interesting that at least these structures in the visual cortex discovered by Hubel and Wiesel have served as a direct inspiration for basically how convolutional architectures work today. So the early precursors of, or maybe the most early precursor of modern convolutional architectures was the neocognitron model. It developed in 1967 by Kunihiko Fukushima. This architecture that he proposed already contained convolutions and downsampling, and was directly inspired by the neuron connectivity discovered in the visual cortex by Hubel and Wiesel. And by the way, it's really interesting that so many of these developments in deep learning or neural network architectures have already started in the 1960s. So if you remember, both the perceptron and the multi-layer perceptron were also developed in the 1960s. And so I think this really goes to show that many of the things that we are implementing now in neural networks were already being researched in the 1960s. So the theoretical foundations were already there, and the theoretical foundations were heavily reliant on the research that was being done in neuroscience. And from my point of view, this is a very interesting connection. So after the 1960s, there wasn't any significant progress in the field of deep learning, which by then wasn't deep learning yet, for a long time. So this changed in 1989 when Yann LeCun, one of the godfathers of deep learning, published this paper, Backpropagation Applied to Handwritten Zip Code Recognition. So those that zip code dataset, by the way, is the same zip code dataset that you got for the exercise sheets, and which is also known as MNIST. And what he did is he used backpropagation to learn convolutional filters of a model. So this was a breakthrough because previously people had mostly been using predefined filters in computer vision. So they had been working with Gaussian filters, for example, or Sobel filters. And Yann LeCun used backpropagation to learn those convolutional filters rather than use predefined ones. And then for another couple of years, there wasn't really any big progress being made in deep learning. I think in 1998, there was another paper by Yann LeCun who published the LeNet architecture. And things really changed in 2012 when AlexNet won the ImageNet challenge. And this is really the moment where the current deep learning revolution started. And so AlexNet combined 3 things that allowed this success. First of all, it used convolutions and downsampling. So this had already been prepared by this neocognitron model. Although, you know, people had already been working with this. I mean, Jan LeCun had also been working this with 1989. So AlexNet was not the first one to rediscover convolutions, but so this was an important feature of the AlexNet model. Then, of course, using backpropagation to train convolutional filters, and finally GPU acceleration. So this is really an important point. I mean, convolutions and backprop, although they are key developments that allowed the deep learning revolution, they were not what triggered the deep learning revolution. So what really did trigger this explosion of depth in neural networks was GPU acceleration, because suddenly people were able to train their networks much faster, and they were also able to train much larger networks. And this hadn't been possible previously. And using this GPU acceleration allowed AlexNet to win the ImageNet challenge by a wide margin compared to its competitors. And it's what basically, so this huge advantage of AlexNet is what created this surge of interest for deep learning and convolutional architectures. Okay, so now enough with the history, and let's start with the theory. And the first question that we need to answer is, what are convolutions and how do we build convolutional architectures? So let's start with the first question: what are convolutions? And so to give you an idea of how convolutions work, I want to look at an example and create a little experiment. So the task at hand is we have an image, not unlike the images that you had in your zip code data set, with something that looks like an 8. And what I want to do is I want to detect whether this image has an 8 digit in it. And well, we're looking for a patch or a sub-window in our image that looks something like this. And now we want to go through our image and see if this patch is present. So what could we do? For example, if we look at this sub-window of our image, we could check whether that feature or whether this sub-window is present there. So we want to compare this sub-window with this sub-window. How do we do that? Well, you've already learned how to do that. We can use a comparison metric, and a useful way of comparing things or vectors in machine learning is using the dot product. So yeah, we can calculate the dot product between this patch and this patch. And in this case, we get a result of -13, which is small. So this seems to indicate that the patch probably does not contain an 8. And now we can just repeat this. So we can shift our sub-window and look at the next sub-window of our full image, and again compare it to the patch that we want to have. And when we do that, so we compute the dot product again. In this case, we would have 5 pixels that are similar to the desired patch, and we get a dot product of -5. So we're getting better, but this still looks very unsimilar to what we want to have. And now we can just repeat this. So we slide our filter or patch over the entire image until finally at some point we end up here. And now if we compute the dot product, we find that all pixels are similar and we get a sum of 15. So since we have the maximum value for the dot product here, this has to be an 8. And we're done. Okay, but so we've been using a very large patch, which was 3 times 5. Maybe we could also use a smaller patch, 3 times 3, for example. So we could, maybe it's enough to just detect this part of the upper half or the lower half for that matter of the 8 instead of the full 8. So let's do a little experiment. So we're going to compute the scalar product with every sub-window of the image as we shift that image, as we shift that sub-window over the entire image. We're going to keep track of the results. We'd start here and compute the dot product for this patch with our respective sub-window. And then we'd shift it along and continue doing the same thing. So now I'm just going to speed forward a little bit. And this is what we get in the end for the result. And well, this result, so if we keep track of our values like that, what we end up in the end is something that looks like a matrix, or if we assign colors or color intensities to these pixels, you find that it's actually just another image. And what's remarkable here is that we have these two bright spots in the center. So this is where the kernel matched the sub-window in our bigger image here at the center. So what are the observations from this experiment? So we see that our operation that we performed has produced a new image of dimension 7 times 7, and the area where the 8 was in the original image is visible as two bright spots in our new image. So that's quite interesting. And the operation that we just performed, that's actually what is called a convolution. So this computing of the dot product and shifting our patch or our kernel, as we call it in the convolutional neural network architectures, this is actually what's a convolution. And let's look at this from a mathematical point of view. So let's call our image, and let's do this for one-dimensional case first. So let's call our image, or in this case, a vector x from Rn. Let's say we have a kernel k from Rm, which should be smaller than my image. And now the convolution is the result of convolving x with k, or the ith entry of the result from convolving x with k can be written as this sum of products xi plus j times kj. So what we do here is we start at the element xi, and then we multiply it with the first element of the kernel, and then we continue with the second element. So now with offset j1, and continue shifting it until we have covered all elements from that kernel. And in 2D, the expression looks pretty much the same, only that now we have a matrix n1 times n2. Our kernel is also a matrix n1 times n2, and now the ijth element of this convolution looks like this. So you see this is pretty much like the expression that we have up here, only that we have an additional index. So now we have xi plus k, j plus l, and our kernel also has two indices. And so if you compare this with a dot product for let's say an input x, and for a linear operation w, so for a matrix from n times m, you notice that the expressions are extremely similar. And actually the similarities between the linear operation and a convolution, or let's say the linear layer that we had with neural networks. So you see this is what we had in logistic regression, for example, don't end there. because convolution is actually also a linear operation. And so the best way to see this is by looking at a 1D convolution. So for our example, let's just say that our kernel W is going to be three-dimensional, and our image, or well, not image, but our vector x on which we apply the kernel is going to be from R5. So this is the vector over here, x1 to x5, and this is this red rectangle represents our kernel. And so in this position, the dot product is just going to be this expression up here. And we can also write this by embedding our W, so by embedding our kernel in a vector from R5 and writing it as a dot product like this. And well, now we can just shift along the kernel, and we do the same thing for for the next position. So now W1 gets multiplied with x2 instead of with x1, W2 with x3 instead of x2, W3 with x4 instead of x3. And now we can again embed this in an R5 vector and have something like this. And finally, we do the final shift. And again, we can represent it as an R5 vector with W embedded in it. So basically what we've done here is we have taken an R5 vector filled with zeros, and then we have shifted our kernel W inside that R5 vector. And then we can represent this as a dot product between our W and the X. And now if we do that for the entire convolution, so we can express this as a matrix product, which would then W convolved with X is equal to a matrix W multiplied with X. And our matrix W would look like this. And so the name of this matrix is Toeplitz matrix. And well, now you know from linear algebra that that a matrix is a representation of a linear map. So in other words, this is a representation of the linear map corresponding to convolution. So we have shown that convolutions are also a type of linear map. And okay, since we are comparing this with matrix multiplications that we are using in linear layers anyway, let's continue this line of thought, and let's put this in a more neuronal way of thinking, or in a more neuronal way, so to speak. So let's keep our example with x coming from R5 and with the output coming from R3. So when we have a linear layer, in order to get this output, we need to have a weight matrix that is from R3 times 5. So it would look like this. And for the convolution, we need to have a kernel from R3. So we get a three-dimensional output, and we just saw in the previous slide that this works. So now let's draw everything as neurons. So we have our input neurons, x1 to x5, and we have our output neurons, y1 to y3. And now let's look at this for the linear layer and for the convolution. So for the linear layer, the output y1 gets contributions from all neurons, from all input neurons, x1 to x5. And the contributions are weighted with weights w11 to w15. Now, if we look at the next neuron, y3, again, we have contributions from all input neurons, x1 to x5, and we have so the contributions are weighted with weights w31 to w35. But what does it look like in the convolution? So in the convolution, our output neuron Y1 only has contributions from 3 input neurons X1 to X3 because we had the kernel. We have the kernel or the sub window only over these 3 neurons, and the contributions that we get from those 3 neurons are weighted with K1, K2, K3. So those are the weights or the entries in the kernel. And now let's look at the last neuron, Y3. So Y3 also gets contributions just from 3 input neurons. And what's interesting here is that the weights, so the weights for those contributions are also K1, K2, K3. So they're not the same. So they're the same weights as for Y1. And this is different from the linear layer, where the contributions for Y1 had weights W11 to W15, and those for Y3 had contributions W31 to W35. So so normally, by default, these weights or these pairs of weights would not be the same, but in a convolution, the weights are by default the same. So let's sum up those two differences that we found. So first of all, we've noticed that convolutions are sparse compared to linear layers. So on the mathematical description level, because we have the triplets matrix, which consists mostly of zeros, at least if the convolution kernel is much smaller than the input image, and this is obviously not the case in the linear layer, because there, by default, those entries are not going to be zeros. And on the neuronal description level, our linear layer has less connectivity than the convolution. And the second difference that we notice is parameter sharing. So in the mathematical description level, every line of the triplets matrix just has the same non-zero values, while in linear layers, well, this is not the case. And on the connection or neuron description level, every convolution output is generated using the same weights. And for linear layers, this is not the case. So Y1 has different weights than Y3. So if we take those two properties together, sparsity and parameter sharing, we get a nice property, namely that we have less parameters. And this is good because, first of all, less parameters means that we are less prone to overfitting due to overparameterization. I mean, basically the reason for this is that when you have many weights in your network or many parameters that you can tune, your model can just learn your data by heart. And obviously this is not good when you have new out of data samples. So when it's possible to have models with less parameters, these tend to be better at generalization than large models. So the second advantage is that we have less memory usage, because obviously it's much cheaper to store a kernel with 3 entries than to store a 3 × 5 matrix. And if we generalize this to arbitrary sizes, this is even more so the case. And so, and further nice properties that we can even have less computational cost if we used optimized architectures, because each output neuron has fewer ingoing connections. So we also need to perform less dot and plus operations. Okay, so far we've looked at a single convolution, but now, since we've already noticed the similarity between linear layers and convolutions, let's also continue the line of thought of neural networks. So if I can use multiple linear layers in neural networks, why not also stack multiple convolution layers to get something like a convolutional architecture? Yeah, that's precisely what we're going to try to do now. I mean, the idea, so the reasoning behind doing this is, so let's remember the example that we had earlier when we had this image with the 8, and we used this convolution or this kernel to calculate this convoluted image. And now when we looked at the convoluted image, we noticed that this image has two bright spots in the center. So we could say, okay, when we have those two bright spots in the center, this is a property that we get when we convolve our image with the 8, so when the feature that we want to have with this kernel. So now we need to build a new kernel that can detect this property or this sub-window in the convolved image. And so the idea would be to define a new convolutional kernel after every convolution that detects a noticeable feature from the previous convolution. But how do we choose those convolution kernels? I mean, obviously, it's not going to be a good idea to just select or to apply my convolutions by hand and then manually decide for one convolution kernel. And so what we need to do is we need to have learnable kernels. So we want to be able to change the parameters of those kernels. And we need to put a loss function at the end to so we can plug the outputs into the loss function and then do backpropagation to tune the weights of our kernels. And the second change that we need to introduce is we need to have nonlinear layers, because remember we just noticed that convolutions are linear operations. So if we just stack one convolution after the other, this is not going to be better than a single linear operation. So to have some nonlinearity and increase the expressive power of such a convolution network, we need to have a nonlinear activation function after every convolution. So this is the kind of architecture that we're aiming to have. So we have convolutional kernels with tunable weights, which get applied on an image. So now we have just one single kernel, but we'll talk about that in a minute. So we apply our convolution, then we apply a nonlinear function f, get an output image, which gets convolved with another kernel. We apply a nonlinear function f on the result, and we just keep repeating those steps until we get that some output that is satisfying, and we plug that into our loss function. And then in the backpropagation step, we can just backpropagate our loss and use the gradients to tune the weights of these convolution kernels. But there's a problem. So right now we've only had one single convolution kernel at each layer. And this is not going to be enough because, well, I mean, we might find a convolution kernel, for example, that works well with the image of the 8 that we just had earlier, but we feed lots of data to our neural networks. And I mean, we want to be able to detect an 8 even if it's tilted, such as here. So we need to account for variance in our data. And well, some of the kernels that we use deeper in the network may only work for an upright 8 and not for a tilted 8. So we need to somehow account for this variance in our data, and we would need kernels that can detect also shifted or tilted and transform 8s. And the second problem is that we may also have input data with multiple channels. So for example, this, I hope you'll agree, looks something like an 8, and it's an RGB image, so it has 3 color channels. And obviously we can't just apply a convolution kernel on 3 different channels. So what we need is a channel for or a kernel for each separate color channel. So how do we tackle those two problems? We need to have multiple filters, and in doing so, we can actually address those two problems because, well, we can have an output channel. We can have an output channel or a kernel, sorry, for each output channel, input channel, sorry. So we can have a kernel for each input channel, and we can have a kernel for each output channel too. and we can interpret the kernels for those output, or we can interpret those output channels, for example, as features that check, or as evaluation results that check, for example, for rotated or transformed properties. So we could have one channel, for example, that is specialized on detecting the upright 8, while another channel is specialized on detecting 8s rotated by 90 degrees. And so, yeah, the solution is just having multiple input and output, or kernels for multiple input and output channels, and then aggregating the results over the input channels. Okay, so this description sounds maybe a bit confusing, but I think a graphical example is going to help you understand what I mean by this. So let's first do a simple example with 3 input channels and just 1 output channel. So our input image has a red, green, and blue channel. So basically we have 3 stacked images, and our convolution kernel also needs to have 1 channel for each of those input channels. So we are going to have a convolution kernel for the red channel, 1 for the green channel, and 1 for the blue channel. And now each of those kernels is going to be convolved with the respective input. So red channel gets convolved with red input channel, green kernel gets convolved with green input channel, and so on. So we get 3 convolved images, and now we just sum all those images together to get 1 single output image with 1 single output channel. Okay, so what would we do if we have not 1 output channel but 2 output channels? Well, the setup would be basically the same. So we still have convolution kernels for each color channel, but now we need to do that for every single output channel. So we have this group of convolution kernels for our first output channel, and we have another group of convolution kernels for our second output channel. And now again, we do the same thing as we did earlier. We convolve each kernel with its respective input image. Now we get a group of output images for the first output channel and for the second output channel. We sum those images together on their respective output channels, and well, now we have an image for the first output channel, 1 image for the second output channel, and if we just stack those images, we get 1 image with 2 output channels. So let's look at this from a more mathematical point of view. I think this is probably going to help you to better understand this. At least for me, it's actually easier to understand this than from the graphical point of view. So earlier in the convolution formula, remember that we had an M1 times M2 kernel, and our formula for the convolution looked like this. But now our convolution kernel not only has a dimension for each pixel dimension, but we also need to have an input channel dimension and an output channel dimension, which we're going to call C in and C out. So our convolution kernel is now M1 times M2 times C in times C out, and well, our expression for the convolution still looks very similar. So we still have the sum over K and over L to M1, and we also our output also still has these indices I and J, but we have an additional output dimension, which is the output channels. And now our input image looks like this. So our input image has these pixel dimensions, but also an input channel dimension. And our kernel has, in addition to the input dimensions, so in addition to the indices K and L, we also have indices D and C out. And we do not only sum over k and l, but we also sum over d. So yeah, so if we try to represent that in a graphical fashion, this is what our x would look like. So the depth in here is the number of channels, so to say, and here we go over the index I plus k. Here we go over the index j plus l. And well, in the convolution kernel, it looks like this. So each kernel has, or the k index goes over the width pixel dimension. Basically, the L goes over the height pixel dimension. And then our D again goes over the channel dimension, input channel dimension, that is. So this would be the colors in our example. And our C out goes over the output channel dimension. So this four-dimensional thing that we had in the previous slide has a name. It's called a tensor. And you might already have heard the name tensor if you have a physics or a mathematics background. But you may also know it from TensorFlow, for example. So yeah, that's where the tensor in TensorFlow comes from. So a tensor is simply a generalization of vectors and matrices. And I think the easiest way to grasp the concept of a tensor for a computer scientist is to think of a tensor of order d as a d-dimensional array. So a zero-dimensional tensor, or actually a zero-order tensor, would be a scalar. A tensor of order 1 would be a vector. So we have just one index I to iterate over the elements of our array or of our tensor. A second order tensor is a matrix, and we have two indices I and j to iterate over the elements. And a 3D tensor is basically a cube of numbers, so to say, where we have three indices to address all entries of our number cube, and each slice along one dimension of that cube gives us a matrix. And yeah, that's pretty much it. So for 4D, it's already really hard to visualize. I did my best on the slide that we had before, but yeah, it's you don't want to paint a four-dimensional object of numbers. Okay, time out. We're halfway through the lecture now. So if you're starting to feel tired, this is probably a good moment to get yourself a cup of coffee, do a couple of push-ups, drink a glass of water, I don't know, whatever helps you. And I'll be back with you in a moment. Okay, I hope that cup of coffee helped, because now we are moving forward with the last part of the lecture. Okay, so so far we've talked about how we can set up a basic convolutional architecture, but if you want to keep up with the terminology of convolutions and convolutional architectures used in modern neural networks, you also need, there's a couple more concepts that you should know. So first of all, remember that we had bias in linear layers, and there's no reason we can not have that in convolution. So a convolution layer, denoted here as a function conv of an input x and a kernel k, is x convolved with my kernel k and plus a bias vector of fitting dimension. And then there's another concept which is called stride, which basically tells us how big the steps are that we can do with the kernel as we slide it over our image. And we have another concept called padding, which tells us if we pad our image or our matrix with additional cells before feeding it to our convolution. Okay, so I'm not talking anymore about the bias because that's straightforward, but let's talk about the stride. So as I said, the stride tells you how many steps you need to slide your convolution kernel. So this is straightforward. So far, we can have a different stride for each dimension. And so far, we've just been doing a 1-1 stride. So we've always been shifting or sliding our image along by one field. So this image convolved with this kernel would give us a 3x3 output image, which looks something like this. And now if we look at a stride of, let's say, 2-1, so we shift our convolution kernel along by 2 on the x-axis, so to say, we get an output image of 2x3. So it would look something like this. I suppose it's pretty clear by now what we mean when we have a stride of 2, and of course we can also have strides that are higher than 2. Okay, so then what's with the padding? So the idea of padding is that we wrap additional cells around our input image, which can be initialized as 0 or with random numbers. And the idea is that they increase the contribution of input border pixels to the output because they increase the output size. So this is what a normal convolution would look like with a padding of 0. And this is the number of times that each kernel, the number of times that each pixel gets touched by that sliding sub window as we compute the output. And now, if we do a padding of 1 with zeros, our input image looks like this, and the number of times that our kernel hits some of these values here increases. And so what happens is that our contributions of these margin pixels here increases, and also the input image by the output image gets larger, and this can be useful in some cases. So there's two modes of padding padding convolutions, which you'll hear about, especially if you work with TensorFlow. There's this valid and so-called same padding mode. So valid seems that we don't use zero padding at all in our convolution, so the input size is reduced after applying the convolution. And this is a problem in neural network architectures, because if we just apply one convolution after the other, the size of our output is going to be reduced in each dimension, and eventually the size of our output is going to hit 0 or 1. And so there's a maximum depth that our networks can reach. But we can tackle that problem using same padding for our convolution. So this means that we have a zero padding around our inputs, and the padding needs to be chosen such that the input size is preserved. So how do we do that? Well, there's this neat formula for the output size of our image. So if we have an input image of size W, a kernel of size K, and padding of size P, and a stride S, then our output image is going to be W, or have dimension W prime, and can be expressed like this. And now if we want to enforce that W is equal to W prime, and we take our stride S and our kernel size K is given, we can just insert this in our formula and then solve this for P, and then we get that P is equal to K minus 1 divided by 2. So this is the usual setting that you have for the padding if you use same padding. And so you may notice here that K needs to be an odd number because otherwise we're not going to be able to divide by 2. And actually, most convolutional architectures have odd-sized kernels, so either 3 or 5, or in some cases even 9. But the most common size that we'll find for kernels is 3. So apparently, there doesn't seem to be a lot of benefit from using even larger convolution kernels because you can just use more convolutions, so build a deeper network and then have smaller kernels that detect more specialized features. Okay, so the convolutional architecture that we designed earlier only had convolutional layers, and an architecture that would look like that would be called fully convolutional, sorry. But there's no reason that we can't also have linear layers. And in fact, a typical architecture that you will find is having first layers of convolutions, and then after our outputs have reached a certain size due to downsampling, we'll also apply a couple of linear layers, typically 2 or 3, which we call head. And I think the reasoning behind this basically is that once you get very deep in your network, the receptive field that the filters have down here is basically going to cover the entire image. So I mean, if we only look at the environment of one receptive filter for a kernel 3, for example, one neuron is looking at three input neurons, but those 3 input neurons also came from a previous convolution kernel, which also looked at or at a neuron, which also looked at 3 inputs. So the receptive field by transition over the entire network is going to be very large. So by transition, basically, deep neurons are looking at a greater patch of the image than neurons that are early in the network. And so since the idea behind our convolutions is that there's a spatial correlation between our inputs. Once you get to the deeper layer of the network, this spatial correlation property really doesn't work anymore, or it's not that prominent anymore, because effectively our neurons are looking at the entire image, and then you can just use a fully connected neuronal architecture. Okay, so so far we only had convolutions, layers or nonlinear layers, and we also motivated that idea with a head. So if you look into modern architectures, for example, AlexNet, you'll find that there's typically some kind of block structure, and we need to use that block structure to get better performance out of our convolutional layers or convolutional architecture. Sorry. So so far so let's start with the obvious part, the convolution layer. So we already know that. Second part is the activation layer. We already know the sigmoid function, but there's actually other functions, activation functions, that can also be used. And in fact, in modern convolutional architectures, we don't use sigmoid anymore, but we use the so-called ReLU function instead. And modern convolutional neural networks would not be as good if it weren't for ReLU. So ReLU is really an important contribution to making convolutional neural networks perform well. Another very important contribution is batch normalization. Actually, this also helps with networks that consist only of linear layers with sigmoid functions. And what these do is that they renormalize the outputs of activation layers for the next block. We'll look into that in a second. And finally, we also have pooling layers, which have the function of shrinking down our output images. So basically, the idea is decoupling the convolution and the downsampling. Okay, let's look into that. Okay, first of all, activation functions. So this one you already know. This is the sigmoid function, and we know what it does. So the function looks like this. It squashes the values from 0 to 1 for the outputs. And it's nice because it's interpretable as probability, but it has some disadvantages. So first of all, our gradients vanish for for inputs that have a large absolute value. So if our x is very small or very large, the gradient is going to become very small, basically 0, because the sigmoid function saturates in that regime. And this is bad if we want to train our network, because small gradients mean small updates in stochastic gradient descent, and small updates mean it's going to take a while to train our network to convergence. Okay, so the second disadvantage is that the sigmoid function is expensive because we need to compute the exponential function. And finally, another disadvantage is that our outputs are not zero-centered. And this is also a disadvantage because, well, if we have negative and positive outputs, after applying the sigmoid function, all our negative outputs are going to become negative inputs, are going to become negative output. So the negative part is just going to vanish, and this might not be a good property to have. And we can solve at least one of those problems using the tanh function, because, well, the tanh function looks basically like the sigmoid function, but it goes from -1 to 1. And, well, going from -1 to 1, obviously the problem of having the outputs not zero-centered isn't there anymore, but it has the other two problems, so vanishing gradients for large absolute values, and it's expensive to compute. So let's see what the ReLU function does. So ReLU stands for rectified linear units, and it's probably one of the most simple functions you could imagine. So what this function does is when your input is smaller than 0, it gets mapped to 0. When it's larger than 0, it gets mapped to itself. This is still a nonlinear function, though, even though it looks like a linear function for x larger than 0. And it has a very nice property, namely that we have non-vanishing gradients for x larger than 0, because the ReLU never saturates, so we always have the same slope, and so we always get big gradients, and we can better train our network. So we can build deeper networks, and we can train our networks faster. But there's a problem. So here, when our x are negative, the output is 0 and the slope is 0, so we do get 0 gradients here. And especially if our inputs are somewhere here, we're going to end up with a dead neuron, because well, since we do not get any gradient update, our neuron is not going to learn anything. So there's going to be no zero gradient. So there's going to be no update of the weight. And the next time that we feed possibly the same input to the network, since nothing has changed, we're still going to get a 0 gradient, and our neuron is not going to update at all. So yeah, this is really a big problem, because ReLU neurons can become dead and just quit, and basically hinder the flow of information through our network, and just avoid our network being updated. So people came up with a slight improvement that solved this problem, namely leaky ReLU. So instead of just setting everything to 0 that is smaller than 0, we also have a linear function here, but scaled with a very small alpha. And yeah, so this has all the good properties that ReLUs also have, but the gradients are bigger than 0 everywhere. So the only point where the gradient is not defined is exactly at 0, but it's very unlikely that you'll have an input exactly here. And our function so we can train our network even when the inputs are negative, and we avoid this problem of having dead neurons. At least it becomes very unlikely to end up with a dead neuron. Okay, so those were activation functions. Now let's talk about batch normalization. So I already said that it's nice to have zero-centered data, and there's actually more reasons to this. So basically neural networks learn much faster when our activations are unit Gaussian distributed, so zero-centered and with a variance of 1. And well, the reason is that most of these activation functions work more nicely when you're close to 0, because being close to 0 means that it takes less steps to optimize your network. And also the nonlinear properties of the networks in many cases become visible around 0. And well, variance. So I mean, if your inputs are very spread out, then, for example, with a sigmoid function, you have many outputs that are in the saturating region. So those aren't going to contribute to updating the gradient. Okay, and the problem is that if you have a very deep neural network, since we are applying so many non-linearities, and our network becomes the network function becomes so complex, typically this is not the case anymore. So you don't have this nice unit Gaussian distribution of outputs. And we want to change that. So the idea is to center and normalize the activations after each convolution and weight layer. I'm not sure you already did this in your past exercise, but normally what people do anyway is that they center and normalize the inputs that they feed to the entire network. And the idea now is to do that, but not just at the input for the entire network, but to do that for the inputs of each intermediate layer. And that's what batch normalization does. So at each intermediate layer, when we look at the output dimension, we compute the mean and the variance of the batch that we are currently feeding through the network. And then we recompute the output for each dimension k like this. So this is just mean shifting. So we compute the mean over dimension k of our batch. We compute the variance over dimension k of our batch, and then we subtract the mean. So we do a mean shift. We reduce we divide by the standard deviation. So we rescale our outputs, and then we multiply this with a parameter gamma and add a parameter beta. Okay, so what is the idea behind these two parameters? I mean, normally we would just, when we normalize our input, we only do this part without the gamma and the beta. And the idea of the beta and the gamma is to be able to go between two extremes of operation. So the first extreme would be to just have default centering on and normalization. So this would be for gamma k equals 1 and beta k equals 0. But in some cases, you may not want to have any batch normalization. And you may just want to feed your unchanged output through the network. So you may just want to keep your xk. And in order to do that, you can learn a beta k and a gamma k that transforms batch normalization into an identity function. So you do this by learning beta k expectation value of the xk's and gamma k variance of the xk's. And when you insert that into the formula here, you will notice that everything cancels out and we're just left with xk. And batch normalization has other nice properties. So it improves the gradient flow through the network, and it reduces the dependence on the weight initialization. Now, one word of advice though. So obviously this is only for training, and this won't work at inference because let's say we just feed one single input through our network. So we have just one single value here for our xk. And well, what's the variance of one single value? It's 0. And the expectation value of a single value is the value itself. So you see that this expression over here is not going to be defined. And so our batch normalization is not going to work. So in order to also make this work in inference, so after we have trained our model, we need to get some estimates for this expectation value here and for the variance here. And we do that by keeping track of the expectation values and the variances that we calculate for each batch, and then after we're done with the training, we just take the mean of those expectation values and the mean of the variances. So basically the mean of the mean and the mean of the variance. And if we define those to be mu k and sigma k, well, we just replace in the above expression our expectation value with the mu k and the variance with the sigma k, or the square root of the variance with the sigma k, and then we can just continue using our batch normalization. Okay, so that was batch normalization. Now finally pooling. Pooling is actually very similar to convolution layer, but with a few changes. So we also slide our window over the image. So we also have a kernel, but it doesn't have any weights. We slide over the image, and instead of applying the dot product between our kernel and the sub window of the image, we aggregate the neighboring pixels. And typical aggregations are maximum. So in that case, we call the pooling operation max pooling, or average. In that case, we call it average pooling. So here, this example is for max pooling with a kernel of dimension 2 times 2 and with a stride of 2. So now in this current position of the kernel, we have the sub window 1395. And if we compute the maximum of those pixels, we would get 9. And then we just slide our kernel and do that for all resulting sub windows, right? So we would get something that looks like this. So I guess this is not very difficult. And the advantage of using pooling layers is that you can decouple the parameter learning, which we do in the convolutions, and we can and the downsampling. So we can just choose this valid padding, for example, for all our convolution layers. So the convolution layers are just busy with learning parameters. And we can do the downsampling step in the pooling layer. So whenever we want to have a downsampling of our output, we would just throw in a pooling layer, and then we will get that downsampling. Okay, so what if we want to build really, really deep networks, such as, for example, the ResNet that we had earlier among the ImageNet windows with 152 layers? Well, in that case, what we have, the methods that we have learned so far are not entirely enough, because we're going to run into two problems. So the first problem is vanishing gradients. And the reason we get that with very deep networks is that, well, if you remember the formulas that we had in backpropagation, let's look at this very simple neural network where we just have one neuron after the other. Now, if we compute the loss, the gradient with respect to x, so derivative of loss with respect to x, and we do this with backprop, you see that we have the derivative of the loss with respect to c, and then this derivative of c to y, derivative y to x. And well, if we trace that down to the first input to our network, we have input b to a, then we'd have c to b, and so on. So we have all those products of gradients. And now if your gradients are very small, smaller than 1, it's clear that this gradient, that is a product of many other gradients, or at least of many other derivatives. So these are not the gradients, but the derivatives. The gradient dl to dA is going to be really small, and really small gradients are bad because that means our updates to the weights are very small, and our network trains slowly and takes a long while to converge. So this is something which we don't want to have. And the second problem is overparameterization. So the deeper your network gets, the more parameters you have, and that's bad because then we tend to have overfitting. So how do we tackle the first problem? Well, this is actually what was done in the ResNet architecture. So that was that brutal model with 152 layers. What they do is that they have so-called residual or skip connections. Basically, the idea is that you have your convolution blocks. So you have a normal convolutional architecture, but then some of the outputs get rerouted around those convolutional blocks and get added to the outputs of the block. So basically, we're just routing around the output. And so on a mathematical level, what this does is an affine transformation. And this is great because it allows us to learn identity mappings. So people thought that if you have a deep neural network, these convolutions should be able to learn identity mappings. I mean, we can tune the parameters, so it should be easy to end up with an identity here if we want to have it. But it turns out this is not the case. And by having this routing around, so apparently it's easier to learn a zero mapping here and to just have this skip connection working as an identity mapping in order to learn an identity mapping for this part of the network. And so other explanations for why residual connections work well is that when you do backprop, obviously you can transport your gradients further back into the network because, your gradient that you get from this node doesn't have to be multiplied with the derivatives that you get from all these layers, but you can just send it back over this connection. And the second, by doing that, our vanishing gradient problem is diminished. And another advantage that residual connections have that was explored only recently is that they smooth the training surface. And smooth training surfaces are great because, if our training surface looks less jittery, there are less local minima where our gradient descent can get stuck in. Okay, so now how do we solve the overfitting problem? So one possible way of doing this is using dropout. And the idea here, again, is extremely simple. So the idea is, let us look at an intermediate layer. So in this example, I did this for an intermediate layer with 4 neurons. And let's look at the output neuron C1, which depends on this intermediate layer. Now, what we want to have is we want to keep neurons with a certain probability p, and we want to drop some of those neurons with a probability 1 minus p. So this is what our input would normally look like, so without dropout in the intermediate layer. So we have C1 getting contributions from Y1, Y2, Y3, and Y4. And now if we do dropout and randomly select these 2 neurons to be dropped, suddenly our output C1 only depends on neurons Y1 and Y3. So our equation for C1 looks like this, and this is what would then be calculated during the training. Then in the next training step, for example, we might select these 2 neurons for dropout, and then our C1 would depend on neurons Y3 and Y4, or get contributions from those 2 neurons. So our expression for C1 would look like this. Now, of course, there's a little trick to applying this, because while we're training, we're only learning with half the neurons. And when we do inference, we want to have all our neurons in the intermediate layer. And well, if we learn this with half the neurons, for example, and then we take all the remaining neurons, of course, the outputs that we're getting during inference at C1 are much bigger than the ones that we're getting during training. So we need to somehow renormalize what is being passed on to C1. And something which works for doing this is just multiplying your outgoing weights with P. So our expression for C1 at inference would look like this. And well, how does dropout work? So what is the interpretation? What is going on here on the conceptual level? Well, the first thing is that in a way it works similar to an ensemble method, because removing neurons and their respective connections is equivalent to changing your network architecture. and we change our network architecture randomly and at every step of the training. So what we're doing effectively is that we are trying out many different architectures in our network, and we are in a way computing an average over all those architectures. But actually this is much better than typical ensemble methods such as bagging or boosting, because we don't need to train our network several times. We just do our training once, and then we expect our network to be some kind of average between all those sub-networks that we had in each training step. And this is really great because we are also able to try out or average over many more architectures that we could possibly have by bagging or boosting instead. And the second interpretation is that dropout works as a regularization because it discourages the network from learning anything by heart. So the idea is, if your network can't rely on individual connections and individual neurons to remember your data, basically, it's not going to try learning the data by heart because it can't rely on the stability of those connections and neurons, but instead it's going to try to learn more general knowledge about your input. Okay, so now let's see what problems we can solve with what we have just learned. So first of all, let me present you a few of benchmark problems for classification. So this one you already know, MNIST. This is the SEP data set that you've been working with. So these are just handwritten digits of 28 times 28 pixels. And well, this was a nice problem for a long time, and it's still a nice problem to set up toy models and see if your ideas are working, but it's too easy for most CNN. So I think currently there's a CNN leading with less than 0.53% error rate in this MNIST challenge. So a data set that's a bit more difficult is the fashion MNIST challenge, which was created at Zalando Research, and where instead of having images of digits, they have grayscale images of clothes, but also 28 times 28 pixels of resolution, and also for 10 classes, only not for 10 classes of digits, but for 10 different classes of clothing. So the idea here was really to make a data set that's as similar to MNIST as possible, but that is more difficult than just regular MNIST. But of course, even fashion MNIST is a toy model. That's not the kind of problems that we really want to solve with more advanced architectures. So something that's more challenging is something such as ImageNet, for which there has been an ongoing competition until 2017. And so this ImageNet datasets consists of 1 million images with 1,000 classes. In total, that makes for 124 gigabytes. So you can see that I think it's very easy to see that this is a far more challenging problem than MNIST, for instance. In fact, if you're doing machine learning just for fun, it may be too challenging. I mean, if you don't have 124 gigabytes to spare and the kind of resources that you need to train models on these huge data sets, well, I suppose you're not going to have a lot of fun. There's also a smaller subsets of ImageNet, for example, ImageNet. The French faux accent is very important here, which is a smaller subset of just 10 classes. And that's nice if you just want to try out ideas for ImageNet before you train on the entire model. So far, we've only talked about classification, but of course, you can't only. Classification problems are not the only problems that are interesting, and there's a whole range of other applications in computer vision that we can tackle with CNNs. So, for example, semantic segmentation. So the idea here is we have an image and we want to subdivide our image in patches that correspond to a certain class of objects. So for example, the purple patch here would be street, and this green patch over here would be tree. And we can do even cooler stuff, such as pose estimation. So we can feed an image of not just one person, but even many people in an image to, and then get an estimation of what their articulation points are like in that scene. And we do it for many people. So that's also a really cool application of CNNs in computer vision. And of course, we're not only limited to computer vision. I mean, convolutions work well for any type of data where we have a lot of spatial correlation. And a spatial correlation doesn't need to mean spatial in the physical sense. So if we have a time correlation, for example, that's also spatial correlation in a sense. So we can also use CNNs for speech and audio recognition to build voice assistants, for example. Or if you want to make a lot of money at the stock market, you can also use it for time series forecasting, for example. So I think CNNs are also going to be also being used in robo-advisors, for example. All right, so that was quite a lot. So let's do a brief summary to get the basic ideas that you should remember about this lecture. So first of all, we've learned that convolutions are linear operations. We've learned that convolutional neural architectures have less connectivity than fully connected architectures with linear layers. And we have learned that convolutional architectures train faster than fully connected networks. And so at the end of the lecture, we've seen that convolutions and skip connections can enable the training of very deep networks that enable higher performance of neural network architectures. Okay, so that's it. That was much longer than I expected this lecture to be. Many concepts, most of them are not very difficult, but it's just the quantity of the concepts is larger than in some other lectures that we've had. Still, I hope you found it the lecture interesting, not too boring, and hopefully not too difficult either. So for the next exercise sheets, you will probably have to implement something in PyTorch. So from now on, we'll be working with PyTorch for all the remaining exercise sheets. And yeah, I know what you're thinking now. Oh my gosh, after this difficult lecture and after learning NumPy, I have to learn a new framework. But you'll see that PyTorch is quite similar to NumPy. And to ease your transition to PyTorch, I've also prepared a small coding session where I'll be covering some of the most basic things that you need to get started with PyTorch. So I'll be doing a small coding example for setting up a neural network for the MNIST challenge that you had as an exercise. And on Monday, I'll be available in the Q&A session to answer both questions about the lecture and that coding session. So if you have questions about the coding session or want to know something more about PyTorch, just feel free to ask me there. Till then, stay safe, stay healthy, and see you. Bye.